and welcome to episode 2 of my course in Noncommutative Algebra. Today, we will be introducing semisimple modules and discussing various examples and properties. As a reminder, last time we discussed simple modules and proved these the key statements. The next level of complexity up from simple modules is, naturally, semisimple modules. We call a module M semisimple if it is a not necessarily finite direct sum of simple modules. Convince yourselves that a module that is isomorphic to a semisimple module is also semisimple. So we will often only show that this definition holds up to isomorphism. The uniqueness theorem for semisimple modules will imply that up to isomorphism of the components, there is a unique way to write a semisimple module as a direct sum of simple modules. But we develop some basic theory before we state and prove that theorem. Just as simple modules behave similarly to one-dimensional vector spaces, which can be seen as spans of basis elements, semisimple modules are of interest because they behave like general vector spaces in many ways, since they are made up of independent one-dimensional vector spaces, quote unquote. They are not to be confused with free modules, which also behave in many ways like vector spaces, although these similarities manifest in different ways. In fact, the notions of semisimple and free module coincide only when R is a field. Namely, with free modules, we are concerned with generalizing the idea of having a basis, i.e. a set of linearly independent spanning vectors, specific vectors, and are concerned with a single given basis, whereas with semisimple modules, we are more concerned with generalizing the fact that vector spaces decompose into a direct sum of one-dimensional, indecomposable subspaces, namely the span of the basis elements. And we do not care about the specific elements in the case of semisimple modules. We now present some elementary examples and non-examples. So any simple module is obviously a semisimple module, so it's just the direct sum of itself. Any vector space is a semisimple module. Just as we said before, take a basis of a vector space V, then V is a direct sum of the spans of each basis vector, giving us a semisimple decomposition of V because the simple modules are the one-dimensional vector spaces. Any direct sum of semisimple modules is, of course, semisimple. And for a less trivial example, let A be a finite abelian group of square-free order. So the prime factorization of the order of A has one factor for each distinct prime appearing in it. So for example, 10 is equal to 2 times 5 is a square-free number. By the primary decomposition theorem for finite abelian groups, A is isomorphic to this, where the pi are distinct primes, and the order of A has a prime decomposition p1 times ... up to pn. So A is a semisimple Z module, since it is a sum of simple modules, i.e. cyclic groups of prime order. Note that not all semisimple Z modules are of this form, so for example the direct sum of 2 copies of Z mod 2Z, because it has non-square free order. Its order is a square. As a non-example, Z as a Z module is free, but is not semisimple. This is because the simple Z modules are isomorphic to Z mod PZ for P are prime, but Z mod PZ does not embed as a submodule of Z, because Z has no finite order elements. For a semisimple, and in fact simple non-free module, consider Z mod PZ as a Z module. It is obviously not free, and we know that it is simple. We will see more meaningful examples later. We will now show that recognizing semisimple modules isn't as hard as it looks. The following proposition tells us that a module is semisimple if every element can be written as a not necessarily unique sum of elements from simple submodules. So if M is a sum of simple modules, Mi for some index set capital I, so not necessarily a direct sum, then M is semisimple if and only if we can extract some independent subfamily, i.e. there is a subset I prime of I, such that M is a direct sum of Mi indexed over I prime. Recall or prove, if you haven't seen this before, that the following conditions are equivalent for a family of submodules. Here they are not necessarily simple, indexed by some index set capital I of a module M. So the mi are independent, i.e. whenever there are finitely many elements, mi1 in capital Mi1 up to mik in capital Mik, such that the sum of these elements is 0, then all of the elements are 0. The second is that the sum of the mi is a direct sum, i.e. every element of it can be written in a unique manner as a sum of finitely many elements from the mi. And the third is that for every I in capital I, we have that mi intersect with the sum of the rest of the submodules is 0. If the mi are simple modules, then these properties are analogous to the notion of linear independence in vector spaces. And in fact, it is linear independence if our ring is a field, so for vector spaces. To understand the previous proposition, note that it essentially says that every module spanned by simple modules will be semisimple, i.e. have a basis of simple submodules. And in particular, one can extract such a basis from a given spanning set, which is exactly analogous to the statement that every spanning set of a vector space contains a basis. In fact, the proof of this proposition is completely analogous to the proof that every spanning set contains a basis. For this, we shall need to recall the unreasonably useful Zorn's lemma. So Zorn's lemma says that if we have a collection of sets P, which we think of as being partially ordered by inclusion of sets, we call a subset T of P a chain if for every two sets in T, one is contained in the other. So suppose that every chain has an upper bound in P, i.e. an element x of P such that every element of the chain is contained within it. Then P has a maximal element, M, which means that there is no element M prime of P which properly contains M. So M is not contained in any other element of P. Note that this is different from M being a maximum, i.e. every element of P is a subset of M. In particular, maximal elements are not unique, which maximums are. And this makes sense if you think of the way the proof goes for vector spaces. Bases are not unique. You can extract several different bases from one linearly independent set, but you just want one of those. We now prove the proposition. Suppose that M is a sum of simple modules mi indexed by capital I. Consider the collection of subsets J of the index set I such that the collection of simple submodules indexed by I is independent, by one of the previous equivalent definitions of independent. We also think of this set as being partially ordered by inclusion. So we call this script f. Every chain in script f has an upper bound in script f, namely the union of all of its elements. Now, clearly, this union is an upper bound, so one must only prove that it is, again, an element of script f. This follows from the fact that independence can be phrased in terms of finite subsets of the index set, and every finite subset of the union of a chain is a subset of one of the elements of the chain. If you haven't seen this type of argument before, I suggest trying to verify the details yourself, namely show that the union X is again an element of script F. So every chain in script F has an upper bound in script F, so by Zorn's lemma, there is a maximal element I prime of script F. Define M prime to be the sum of the mi indexed over I prime. We claim that M prime is equal to M. For every index j, mj is a simple module. Hence, either the intersection of mj with M prime is 0, or it is equal to mj, since it is a submodule of mj. If the intersection of mj with M prime is 0, then mj is independent of M prime, and hence independent of the family of submodules indexed by I prime. Feel free to pause and try and prove this, or read the argument presented on screen. This means that I prime union j is in script f, a contradiction to the maximality of I prime. We must therefore have that the intersection of mj with M prime for all j in I is mj, but this implies that mj is a submodule of M prime for all j. Hence, the sum of all mj is also a submodule of M prime, but this is equal to M by hypothesis. So M prime contains M and hence is equal to it, and so M is semisimple. We now have the following useful corollary. If M is semisimple, every submodule and every quotient of M is also semisimple. For the proof, we first prove that every quotient is semisimple. Let M be the direct sum of mi indexed over capital I, and let M prime be a submodule. Suppose that M prime is non-zero and not equal to all of M, as otherwise the corollary is trivial, because the quotient is either going to be 0 or isomorphic to all of M. Consider the quotient map pi going from M to M mod M prime. For every index I in capital I, if the image of mi under pi is non-zero, then it is isomorphic to mi, since the restriction of pi to mi will always be injective, as the kernel is a submodule of mi and mi is simple, hence it will be an isomorphism onto its image. So pi of mi is simple whenever it is non-zero. Note that M mod M prime is equal to the sum of the pi mi indexed over capital I. This is because pi is a surjective homomorphism, so its image is the whole of M mod M prime, and it of course preserves sums, and M is the sum of the mi. Since M mod M prime is non-zero by assumption, there exists at least one index I such that pi of mi is non-zero. So we get that M mod M prime is equal to the sum of all the non-zero pi of mi's, which are simple modules. Hence M mod M prime is semi-simple by the previous proposition, since it's a sum of simple modules. In particular, there exists a subset I double prime of the index set I, such that M mod M prime is the direct sum of the pi of mi, indexed over I double prime. In fact, we claim that M mod M prime is isomorphic to the direct sum of mi indexed over I double prime. We will call the right-hand side M double prime. Moreover, this isomorphism is the restriction of the projection to M double prime. Indeed, surjectivity is obvious from equation 1. If M is an element of M mod M prime, then by equation 1 there exist distinct indices I1 up to In in I double prime, where n is some arbitrary natural number, and elements mk of the simple modules indexed by these I1 up to In, such that M is equal to the sum pi of M1 up to pi of Mn, which of course by pi being a homomorphism is equal to pi of the sum of M1 up to Mn, but M1 plus ... plus Mn is an element of M double prime. So M is an image of M double prime under pi, since it is equal to this expression. Hence pi restricted to M double prime is surjective. Next, we prove injectivity. Suppose that M is an element of M double prime, such that pi of M is 0, i.e. M is in the kernel of pi. Recall that M double prime is the direct sum of Mi indexed over I double prime, by definition. Similar to before, we can write M as a sum of M1 up to Mn for Mi in simple modules indexed by I1 up to In, indices in I double prime. We now apply pi and use our assumption to get that the sum of pi of M1 up to pi of Mn is 0 by equation 1. Independence of the direct sum gives that all of the images of M1 up to Mn are equal to 0. But we know that pi restricted to each simple module Mi is an isomorphism. Hence, M1 up to Mn are all equal to 0, but this means that M is also equal to 0, so pi is injective and hence an isomorphism. Next, we claim that M is the direct sum of M prime and M double prime. First, we check that M prime and M double prime are independent, or equivalently, their intersection is the 0 module. If an element M is in the intersection, then its image under pi is 0, since it's an M prime, but pi restricted to M double prime is an isomorphism, and M is an M double prime. Hence, since it is sent to 0, it must be 0 itself. So the intersection is 0. Next, we show that the entire module is the sum of M prime and M double prime. Let M be any element of the module and consider its image under pi. Just as before, we can write pi as a sum of images of elements mk of mik for k from 1 up to n, so we get that since the images of m and m1 plus ... up to mn are the same, the image of their difference, which we shall call m prime, is 0. But this means that m prime is in the submodule capital M prime. So we can write m as the sum of an element of m prime and an element of m double prime. Hence m is the direct sum of m prime and m double prime. Let I prime be the set difference between I and I double prime. We claim that m prime is isomorphic to the direct sum of mi indexed over I prime, and hence semi-simple. We know that we can write m as the direct sum over all of I, so we can split it to the I double prime part, which is m double prime, and the I prime part. The natural projection Q coming from the direct sum onto the I prime component has kernel m double prime by definition, since it's given by decomposing an element as a sum of elements of m double prime and an element of the direct sum of mi indexed over I prime, and then throwing away the m double prime component. Hence, by the first isomorphism theorem, we get an isomorphism of m mod m double prime with the direct sum of mi indexed over I prime. A similar argument for the natural projection from the direct sum of m prime and m double prime onto m prime gives us that m mod m prime is isomorphic to m prime as well. So we get the desired isomorphism between m prime and the direct sum over I prime, since they are both isomorphic to m mod m double prime. Hence, m prime is semi-simple, so we are done. We now state the uniqueness theorem. Let M be a semi-simple module, and suppose that M has two semi-simple decompositions indexed by I and J. Then the index sets I and J have the same cardinality, i.e. both decompositions have the same number of components, and furthermore, there is a bijection from capital I to capital J such that Mi is isomorphic to M prime pi I. So pi associates to each index J in capital J a unique index I in capital I such that the corresponding simple modules are isomorphic. Note that such a bijection is usually not unique, since M's semi-simple decomposition may contain multiple simple modules, as in the case of vector spaces, since all one-dimensional vector spaces are isomorphic. So for example, if mi1 and mi2 are isomorphic for some i1, i2 distinct indices in I, we can define a new bijection, tau, satisfying the conditions of the theorem as follows. Note that the theorem is not true if we upgrade the requirement of isomorphism of the simple components to equality, even if we require the semi-simple decompositions to actually be equal instead of isomorphic. For example, there are infinitely many ways to decompose R2 into a direct sum of two simple R modules by taking just infinitely many non-proportional bases. The sketch of the proof is as follows. Suppose that we have an isomorphism F between two different semi-simple decompositions. We first use Scher's lemma to show that there is an index J1 such that M1 is isomorphic to MJ1 prime. Define pi of 1 to be J1. We would now like to quotient out by M1 on the left-hand side and MJ1 prime on the right-hand side, using the first isomorphism theorem. For this, we show that we can replace MJ1 prime by the image of M1 under F, i.e. this F of M1 forms a direct sum with the rest of the MJ prime. Note that this is actually an equality and not just an isomorphism. We now use the above equality together with the first isomorphism theorem to get an isomorphism of semi-simple modules with fewer components, so n-1 on the left-hand side and m-1 on the right-hand side. So the left-hand side does not have m1 and the right-hand side does not have mj1 prime. We continue by induction, each time finding a module mji prime isomorphic to mi for the next index I. Then we define pi of I equals ji, until we are left with an isomorphism of mn, the final component on the left-hand side, to a direct sum of m minus n plus 1 simple modules. And without loss of generality, I'm assuming n is less than or equal to m. A simple module cannot be a direct sum of more than one simple module, since this gives non-trivial submodules. So we must have that n is equal to m. And pi, defined by pi of I equals ji, is the required bijection. We finish our introduction to semi-simple modules with the following useful characterization. Let M be a non-zero module. M is semi-simple if and only if every submodule has a complement, i.e. if n is a submodule, there is a submodule P such that the n and P are independent and the sum is all of F, so they form a direct sum. We leave the proof of the heart direction as a guided exercise below. The other direction, i.e. that every submodule of a semi-simple module has a complement, was inadvertently proven as part of the proof of corollary 1.9. Recall that to prove that a submodule M prime is semi-simple, we first showed that it had a complement M double prime. I will now leave the guided exercise on screen. It also appears in the notes in the description. We also note that this proposition does not generally hold for free modules, even though it holds for vector spaces. So, as analogies to vector spaces, this is one advantage of semi-simple modules over free modules, because it has this extra property of vector spaces. That ends our first foray into semi-simple modules. Next time, we will discuss the endomorphism rings of semi-simple modules. Thank you for watching, and we'll see you next time.